Hey physicists, so here's scenario 3. So this one's a little bit different, but I think you're gonna like it. So going through a looping coaster, it says the minimum speed needed to safely compete the loop of a particular looping roller coaster and not fall out is 8.9 meters per second. And so then there are two parts. It says part A, based on this, determine the radius of the first loop. Hint, the speed of the car, as the speed of the car decreases, does the centripetal acceleration increase or decrease? Does the force of gravity change? How does the other force change? So that hint is going to kind of help us work through the problem. But before we do any sort of mathematics, we probably need to draw a picture. So we're going to go down here and on the free body diagram, go ahead and draw our forces. So again, just to kind of keep our brains in what's going on, I'm going to draw, this is not part of the free body diagram, but just to get your head around what we're doing. This is like the top of the loop, okay? So at the very top of the loop, what forces are acting? Well, the force of gravity is always acting, right? The force of the earth. So I'm going to go ahead and draw that one down here. The force of the earth on, I'm going to call it just a car, the roller coaster car, okay? And then any other forces acting, so this is kind of like when we were swinging the water around. In the water cup example, the tension was pulling down. If you've ever been on a looping roller coaster, you know there's no tension pulling you down, but the coaster itself is actually pushing down on the car. So there is another force actually pushing down. Okay, that's the force of the track on the car, and that's a normal force. Okay, so that force is actually pushing down. Now, for those of you that don't like looping roller coasters, that might be a little bit frightening to think about the fact that there's nothing pushing you out as you're going around that loop. But as you know, as long as you have that tangential velocity, you're going to be okay. So there are no other forces acting. I'm going to go ahead and write down my F-net equations here. So if we look carefully at the free body diagram, there are no forces acting in the x direction. But there are two forces acting in the y direction, aren't there? So we've got the normal force, and, oops, and that one's going down. And we've got the force of gravity. And yes, indeed, we are accelerating. And in fact, that acceleration is towards the center of the circle, which is downward. But just a friendly reminder that you still got that tangential velocity, which is why you don't fall down when you're up at the top. Okay, oops. Sorry about that. Okay, so that's kind of what we know. It says in the problem that the minimum speed we need is 8.9 meters per second. So that's kind of an interesting thing that we're talking about here. Whoops, right, V, not W, excuse me. V minimum is 8.9 meters per second, okay? And they wanted to know then the radius. So that's our unknown. Okay, so the hint now is going to come into play. So there is, as we're saying, a minimum speed. So the faster you go, the higher your centripetal acceleration will be, the higher that net force will be. But the slower you go, the lower that centripetal acceleration is going to be. The force of gravity is equal to m times g, right? We know that. And that's not going to change depending on your speed. So the thing that can change is the normal force. And in order to get this thing right here to be as small as possible, the normal force is going to have to be as small as possible. So for part A, to get to that minimum speed, that means the normal force is going to go to 0. Okay, a little bit funny, but again, that's just to find that minimum. So we've got the force of gravity. Whoa, I don't know here. There we go. So the minimum centripetal acceleration will be when the force of gravity is the only force acting. So we've got m times a sub c. And now we can use that to find our radius. You can see that the masses are going to cancel, which is nice. That means that no matter how big or small you are, how big or small the car is, the radius isn't going to be dependent. So we've got g is equal to a sub c, remembering that a sub c is v squared over r, and so we can solve that for the radius. So the radius for this circle with a minimum speed of 8.9 is going to be equal to v squared over g. And we can just plug in our numbers. So we've got 8.9 meters per second. We're going to square that value and then divide by 9.8 meters per second squared. Okay, and then plug that in. And when you do that, I got something like 8.08 meters. Okay, so that's just telling us the radius of the loop itself. Okay, that's what that value is telling us. So that's part A, and that's just kind of finding that minimum, just for fun. Okay, that's what a roller coaster designer would have to work on. The rest of this is more similar to the other questions that we've worked on. So it says the roller coaster actually moves faster than the minimum speed. That's good to know. Okay, so it's actually going to move at 12.2 meters per second through the loop. And then it asks us to determine the centripetal acceleration they'll experience based on the car's actuals. So in this case, then, it says we're just looking for centripetal acceleration. That's a sub c, which remember we said is v squared over r. Don't have to do a lot with the forces in this problem because we know the velocity is 12.2. Oops, it's going to be a good kid and write all that down. Meters per second, quantity squared, divided by the radius, which we now know is 8.08 meters. Please get out your calculators. You guys work on this too. Again, remember to square that speed, and hopefully you get something about 18.4 meters per second squared. There you go. Hop on to the next one. Have a great day.